Okay, so now I want to refer about the fact that what we saw before, we find the optimal point for the dual. But what we want to tell you about now is the limit of this method of PPT, and yeah, basically what we want to say is like the SDP, like semi-definite programming, coupled to PPT for relaxation is a really cool method for characterize and detect integration for 2-qubit system, because the PPT is literally equal to the seperable ensemble. So yeah, but if we have like super dimensions, the transposition cannot be sufficient anymore, and we will need to test an infinity of positive application but non completely positive to characterize the separability. That's illustrate why this problem is NP hard, you know, at a big scale. So yeah, what I want you to drive about is like also like it's really powerful in this 2-qubit case, because no matter theta, it works for all the states in the family. Like in the precedent calculus, in the last video, we just find that W star matrix does not contain any parameter theta. Yeah, it does not contain any parameter theta, but yeah, it does not contain any parameter theta. But the fact is, it means like we can choose any data between 0 and p/4. That's why we say like this problem is robust and optimal for weak duality. And also, I want also to emphasize the fact that the partial transposition was able to detect integration, because transposition is a positive application but not a completely positive one. It means like if it is positive, if you apply it into an isolated system, a positive matrix will still be positive. She does not create negative probabilities, but in this case it's like positive but not completely positive, and so the system is entangled with another one, like either qubit A or qubit B, and so applicate the transposition only on A or only on B can destroy the global positivity and be able to make appear some eigenvalues which are negative, and so yeah, that will be able to detect so the entanglement. So yeah, basically we can do this by transposition, but we can do this with no matter any other application that is positive but not completely positive, because it's a linear application, the calcul will be the same translation to an SDP problem. Even more theoretical and more further, if we were to take the intersection of all PP stuff sets, then you will get the set of separable states. Like if we take all positive application non-completely positive existing into the universe of mathematics, it will create a relaxation ensemble for every one of them. And the geometrical intersection of all those ensembles will be exactly the set of separable states. So yeah, I said ensemble is just a set, like yeah. So we say, so as I said at the beginning, we still say this problem is NP-hard because in dimension like of C2 or C2 um, or C2 or C3 is a complex number, transposition alone will be sufficient. The set of PPT is literally equal to a seperable state. Um, yeah, PPT set equals for the set. But that's why this is working perfectly. But if we go to much bigger system, like good thread system, PPT state will be bigger. PPT set will be bigger than separable state, and there will exist some integrated, some untoggled states that will still stay in PPT. And to reiterate the separable set, we will need the intersection of an infinity of unstable PP application. So yeah, that's why a computer cannot do it in practice for bigger dimension, because we cannot do an infinity of SDP constraints. So yeah, that's basically what I said at the beginning. So SDP with PPT is a really cool and method which has his strengths to detect entanglements in of a system of 2 qubits, because the state of PPT is equal to the ensemble, because the set PPT is equal to the set of the several sets. But for a bigger dimension, transposition will be not sufficient alone. We will need to test an affinity of application positive but not completely positive to know about separability, which illustrates the NP hardness of this problem.